Hello dear students, let us continue with the portion of functional analysis. So in the previous session we have discussed some of the important definitions, that is Banach algebra and normed algebra, or we can say that normed linear algebra, isn't it? So before that we have seen what is algebra. First let us recall the definition of algebra, normed algebra, then we will continue with the theorem which we were solving in the previous session. Okay, so the definition of algebra says that if I consider n as a linear space and if I choose some vectors in n, say x comma y belongs to n, then these vectors should satisfy some of the multiplication properties, right? This is what we have seen in the previous session. That is, the first condition is x into yz is equal to x y into z. The second condition is x into y plus z is equal to xy plus zy, or we can write x plus y into z is equal to xz plus yz. And one more condition is alpha into xy, this will be equal to alpha x into y, or we can write this as x into alpha y, where your alpha belongs to scalar, say r, isn't it? So if these three conditions are satisfied, then I can say that the linear space n is an algebra. Along with these three conditions, if one more condition, that is norm xy is less than or equal to norm x into norm y, then I can say that this is a normed linear algebra. So this is the major difference between algebra and normed linear algebra, or simply a normed algebra. So one more definition we have seen is Banach algebra, right? So how we can define our Banach algebra? Any real or complex Banach space is also a normed algebra then we can say that as a Banach algebra. This is how we defined these three major terms: algebra, normed algebra and Banach algebra, right? Using this concept we were proving one theorem. So let's recall the theorem also, then I will continue with the left out part. Okay. The statement of the theorem is, suppose that the Banach space is the direct sum of the linear subspace m and n, so that B is equal to m direct sum n, and let z is equal to x plus y be the unique expression of a vector z in B as the sum of vectors x and y in m and n. We have to show that a new norm can be defined on the linear space B by norm z whole prime is equal to norm x plus norm y. And also we have to verify that this new norm is actually a norm. That means we have to prove the four conditions of normed linear space. Also they have given one more thing, that is, if B prime symbolizes the linear space equipped with this norm, prove that B prime is a Banach space if m and n are closed in B. This is what the given statement. So since B and B prime are same sets, we can say that if B is equal to direct sum of m and n, and I can represent z as x plus y, which is a unique representation, I can say that norm z prime is also equal to norm x plus norm y. This is already a normed space, right? Since norm is continuous, or using those concepts we can say that norm z prime is equal to norm x plus norm y. You need not to prove this part because in the given data only they have given that z is equal to x plus y. So if this is an unique representation in the Banach space of your M and N, then obviously this thing holds. So you need not to prove this. That's why we directly went to prove the normed linear space points. Okay, so here what we have done, initially we have taken z, z1, z2 which are coming from the space B prime. So from the given data, since I can represent z as x plus y, I can write z is equal to x plus y, z1 is equal to x1 plus y1 and z2 is equal to x2 plus y2, where your x, x1, x2 are coming from the space M and y, y1, y2 are coming from the space N, isn't it? So now we will consider one more scalar quantity, that is alpha, which is nothing but your field. So the first condition is norm z prime is greater than or equal to 0. We know that I can represent norm z prime as norm x plus norm y. Since norm z prime is greater than or equal to 0, this implies norm x, norm y both are greater than or equal to 0. So from that I can say that this is the obvious condition. So the next condition is, we have to prove that if norm z prime is equal to 0, then this implies z is equal to 0. Also vice versa, right? So for that what we have taken, first I have taken norm z prime is equal to 0. Since I can represent norm z prime as norm x plus norm y, this obviously equal to 0. So if sum of this is equal to 0, then I can say that individually norm x is 0 and norm y is 0. Right? So if norm x and norm y is 0, we can say that x is equal to 0 and y is equal to 0. So from this z will be obviously 0. So this is our second condition, and the third condition is norm z1 plus z2 prime. We have to prove this whole part is less than or equal to norm z1 prime plus norm z2 prime. So for that what we have done, first I have just substituted the value of z1 and z2. So again we can group this as x1 plus x2 plus y1 plus y2. Since norm z1 prime is equal to norm x plus norm y, if we are splitting this means this prime will not be there in this step. So don't get confused, okay? This is like, this is my z1 now and this is my z2. So this is something like z1 plus z2 whole prime. So if I am splitting this modulus or norm means I will get inequality. So norm z1 plus norm z2. In this way we are splitting this, okay? So now again grouping the terms, norm x1 plus norm x2 plus norm y1 plus norm y2. Here I am just grouping norm x1 plus norm y1 plus norm x2 plus norm y2. We know that this is nothing but norm z1 prime. This third and fourth term is nothing but norm z2 prime. So from this we can say that our LHS part is less than or equal to sum of norm z1 prime and norm z2 prime. So this is our third condition. Now the fourth condition is norm alpha z whole prime is equal to mod alpha into norm z prime. This is what we have to prove, right? So for that again substitute the value of z. Z is nothing but x plus y. Using scalar multiplication we can write alpha x plus alpha y. So norm alpha z prime is equal to norm alpha x plus norm alpha y. Now again since alpha is scalar, we can write this as mod alpha into norm x, mod alpha into norm y. So I can take out mod alpha as common, you will get norm x plus norm y. So this is nothing but norm z prime. Right? So from these four conditions we can say that B prime is a normed linear space. So one more thing we are left out to prove, that is we have to prove that B prime is complete. So how to prove the completeness? First I have to consider a sequence which is a Cauchy's sequence in B prime, and I have to prove that the converging point of this Cauchy's sequence is also belongs to B prime. Then I can say that my B prime is complete, right? So let's prove that part now. We have M and N as closed subspaces of complete space, right? So this implies M and N are complete. Now I will consider a Cauchy sequence in B prime. So the Cauchy sequence will be in the form of Zn, and we know that I can express Zn as xn plus yn, where xn belongs to M and yn belongs to N, isn't it? So now using the definition of Cauchy's sequence, we can write that Zn minus Zm will be equal to xn plus yn minus xm plus ym. So this is nothing but xn minus xm plus, just grouping the terms, yn minus ym. Okay. So now this thing I will use in the next part. Now I will consider the definition of Cauchy sequence. Using the Cauchy sequence, I can say that there exists some point n0 and belongs to n such that m comma n is greater than or equal to n0. This implies norm Zn minus Zm whole prime will be less than epsilon, right? So now I know what is Zn minus Zm. I can substitute here. So this implies norm xn minus xm plus norm yn minus ym. This thing will be less than epsilon, right? So if the sum of these two is less than epsilon, then I can say that norm xn minus xm will be less than epsilon by 2, and norm yn minus ym is also less than epsilon by 2, where your n and m will be greater than or equal to the point n0, right? So now since sequence xn is Cauchy's sequence in M and sequence yn is a Cauchy's sequence in N, and M and N are complete, we can say that there exists some point P belongs to M and some point Q belongs to N such that our xn converges to that point P and yn converges to Q. I repeat, we know that xn and xn belongs to M and yn belongs to N, right? So xn belongs to M and yn belongs to N. We know that M and N are complete. From the definition of completeness, we know that there exists a converging point, or you can say that limiting point in the same spaces, right? So for that purpose, I can say that xn converges to some point and that point is P, yn converges to some point and that point is Q, where this P belongs to M and Q belongs to N, right? So now if I take xn plus yn, obviously this converges to some point, say P plus Q. What is xn plus yn now? This is nothing but my Zn, and Zn converges to some point P plus Q. We know that B is equal to direct sum of M plus N, right? Using this concept, I can take sum of these two sequences and I can say that sum of these two sequences converges to some point, and that point we are indicating as P plus Q, okay? Now from this, what I can say, this P plus Q belongs to the space B prime. So from this we can say that we have considered the sequence Zn in B prime and its converging point P plus Q is also in B prime. So I can conclude that B prime is complete. Alright, from the first part of the proof we know that B prime is a normed linear space, and from the second part we can say that B prime is complete. So using these two I can say that B prime is a Banach space. So this is how we prove this theorem. Hope the theorem is clear to all of you. Now let's move to the next important topic, that is functional conjugate space. So how we can define functional conjugate space? First I will consider a N which is a normed linear space. Okay. Obviously this is a normed linear space over a field K which contains scalars, right? And I can represent this K as R or C. That is nothing but a real normed linear space or a complex normed linear space. So if any continuous linear map from, I will denote that map as F, from N to K, that is either R or C. Any continuous linear map F from N to K we called as a functional. Okay, so the set of all functionals, this is one functional. Similarly, if I collect all the set of functionals and if I make that as one set, then I will denote that set as N star. This N star is called as conjugate space of N. I repeat. So first, what any mapping, okay, any mapping F from N to K is said to be functional, where N is a normed linear space over the field K, where K contains all scalar values and that K may be a real or complex. The set of all such functionals, if I denote this as F1 from N to K, F2 from N to K, F3 from N to K. So the set of all such functionals we will denote as N star, and this N star is called as conjugate space of N. So I can say that this N star is a set consists of set of functionals. N star is a space, okay. So N star is a space which consists of all functionals. Then you can call that N star as conjugate space of N. Okay. So similarly, if N star whole star is equal to, I can denote N star whole star as N double star, and this N double star is called as second conjugate space of N. That means again the set of all N stars can be denoted as N double star, and this N double star is called as second conjugate space of N. This is how we define functional and conjugate space. Okay. The next important definition is isometric isomorphism. So here also we will consider a mapping set T from N to M, where your N and M are normed linear spaces. Okay. I can say this T as an isometric isomorphism if this T is 1 1 and if norm T of x is equal to norm x for all the values of x belongs to n. If these two conditions are true, then I can say that T is an isometric isomorphism. The next definition is extension of linear functional. So as the name suggests, there is an extension in a function. So we can define this as, if I consider n as a normed linear space and M as a subspace of n, if I consider or if I define a function and its elements say x belongs to M, that is we can define norm Fm as supremum of f of x such that x belongs to M and norm x is less than or equal to 1. So for example, we are defining some function in this way which is in the space M, that is a subspace of your normed linear space n. If I extend this function to the whole space n, then I can say that f is a extension of linear function. That means f of x is equal to f of x. That is nothing but, let us consider this is my subspace M, okay, and this is the space n. If we are defining a function f in this space, we are defining function, along with that we are defining norm, right? If I defining norm in this space, say M which is a subspace of n, and if I extend that to the whole part of the space, then I can say that f is an extension of linear functional, and I will denote that as f of x is equal to capital F of x for all x belongs to M. So this is how we define our extension linear functional, okay. So now using these three definitions, now let's prove one of the major important theorem in your functional analysis. That is nothing but Hahn-Banach theorem. The statement of the theorem says that let M be a linear subspace of a normed linear space n, let f be a linear functional on M, then f can be extended to a function f defined on the whole space n such that norm f is equal to norm f. So from the statement I can write that M is my linear subspace of n and f is a linear functional on M. If this is the given data, then I have to prove that f can be extended to a function f defined on whole space n, right, such that norm f is equal to norm f. This is what we have to prove. In order to prove this part, I have to use one lemma, because here first I have to check whether I can extend the function in my subspace. If I can extend, then I can, if the conditions are true in M space, then I can extend to N. So first I have to check for M. In order to check for M, we will use one more theorem, that is a supporting lemma for the Hahn-Banach theorem. Okay, the statement of lemma says that let M be a linear subspace of a normed linear space N, and x0 belongs to N and x0 does not belongs to M. Let f be a functional on M. Okay, if m0, if we can represent m0 as M union x0, which is equal to x plus alpha x0, and x belongs to M, alpha is real, is the linear subspace generated by M and x0, then f can be extended to a functional f0 defined on m0 such that norm f0 is equal to norm f. So this is first part of the proof for your Hahn-Banach theorem. I have to prove this part first, then I can extend to the whole space. Before extending to whole space, we have to check for the subspace, right? So for that we are using this lemma. So according to the statement of the lemma, we can write M is a linear subspace x0 is some point in N and this x0 does not belongs to M. So we can write a set m0 as M union x0, which is equal to x plus alpha x0 such that x belongs to M and alpha is some real value, right? So here you can observe m0 consists the point of x0, but M does not contains x0. That's why in order to denote m0, we have written M union x0. That means this m0 space is including the point x0. Okay. So first thing what we have to do, since f is a functional and we have to extend the functional f to f0, let's define a mapping f0 from subspace M to scalar k. Okay. We are writing this mapping using the definition of functional. So this k, in the statement of the theorem, they have not mentioned whether k is real or complex. So in order to prove this theorem, we have two cases. One is k is real and another one is k is complex. Okay. So first what I will do is, I will consider my N as a real normed linear space. That is, N is a real normed linear space. So using this definition, we can write that if I choose some u, an arbitrary vector u as x plus alpha x0, I can write f naught of u is equal to f naught of x plus alpha x0. This will be equal to, so in the whole thing will map to the real value. I will denote that as f of x plus alpha r naught. Okay. So here this r naught is some arbitrary value which is coming from your real number r. Now let's consider some points in M. That is, I will choose 2 points u and v in M0, and using the definition of M0, I can represent u as x plus alpha x0 and v as y plus beta x0, right? So now we have 2 more vectors x and y which are coming from M, and we have to consider scalars say a and b which belongs to R. because n is a real normed linear space in this proof. Now let's prove f0 is linear in the first place. Okay, in order to prove the linearity property, first I will consider AU plus BV. What is AU plus BV now? A into U is x plus alpha x naught plus B into y plus beta x naught. So we can rewrite this as AX plus BY plus x naught into A alpha plus B beta, right? Where your AX plus BY belongs to the space M and AB belongs to R. So now if you operate F0, this will become F0 of AU plus BV, which will be F0 of AX plus BY plus x naught into A alpha plus B beta. This is nothing but, again you can use the definition, that is f0 of u is equal to f0 of x plus alpha x naught. This is mapped to some value, real value, that is f of x plus alpha r naught. Using this definition, we can rewrite this as f of ax plus by plus a alpha plus b beta into r naught, as f is linear. Now this is nothing but a into f of x plus b into f of y. I will retain this part as it is. So group the terms. We can write this as a into f of x plus alpha r naught plus b into f of y plus beta r naught, right? This is nothing but, now this whole thing can be again rewritten in this form, f0 of x plus alpha x naught. So this is nothing but a into f0 of x plus alpha x naught plus b into f0 of y plus beta x naught. From the defined u and v, we know that u is equal to x plus alpha x naught and v is equal to y plus beta x naught. So using that, we can write this as a into f0 of u plus b into f0 of v. In the LHS part, we have f0 of au plus bv. So from this, we can say that f0 is linear. Now from this we can say that your defined thing is there, right? This is, I will call this as equation number 1. From this we can say that f0 is linear functional on m0, not on m or n. Okay, this is on m0. And from this we can say that f0 of x is equal to f of x for all x belongs to m if you consider alpha as 0. In this, I will call this as your equation number 2. Or in order to avoid confusion, you can just check here only. If you consider alpha is equal to 0, then you can say that f0 is equal to f, right? Or f0 of x is equal to f of x in this. That means you can say that you can extend your function f0. f0 is an extension of your function f. So one part of the proof is over in your lemma. That is, we have proved that f can be extended to a functional f0. Now we have to prove that norm f0 is equal to norm f. So we can prove this in one way, that is, First I will prove norm f naught is greater than or equal to norm f. In the second part I will prove norm f naught is less than or equal to norm f. Then from these two we can conclude that norm f naught is equal to norm f. Okay, this is how we can prove this part. I repeat, just check the statement once again. If this is the given data, first we have to prove that f can be extended to a functional f naught defined on m naught. So this is the functional which is defined on m naught. If I prove f naught of x is equal to f of x, then I can say that f is an extension of your f naught, right? And one more part they have given in the theorem to prove, that is norm f naught is equal to norm f. In order to prove this, we will prove these two parts, and from these two parts we can conclude that norm f naught is equal to norm f. I will continue with this part in the next session. Thank you.